Okay, now, what we're doing, we're getting into a fairly extensive review of the course. And I have all this stuff. Yeah. Okay. We just, saying this for the camera because I already said it to everybody, but we just went over a bunch of stuff in the support course. Okay. And a few people refer my students to the support course to see the full video, but I'm going to go over it in about 10 minutes. We're going to start with this, which is typical of some of the problems you might see on the test. And we'll go with a few more examples like this after we go over the algebra solving some equations. We started with 3 points. A point here, point here, and a point here. And I drew a parabola through those 3 points. Given any 3 points, as long as none of them are right above each other, 3 points with different x coordinates, you can always sketch a parabola that goes through those 3 points, and you can always get the equation of that parabola, which I'm probably going to talk about in a minute. Okay. So here's a parabola. I drew the axis of symmetry. I put a scale on it. We said y is 7 about here at the y-intercept. X was 1 at this point. X was 10 at this point. So we estimated X was 5 at this point. So we put the lines X equals 1, X equals 5, X equals 10 down there. And then we estimated the coordinates of the vertex, which is on the axis of symmetry, which is kind of close to one of the points that we drew, but not exactly. We want to estimate where the axis of symmetry is, cut this thing in half as best we can, get the vertex. We estimated the vertex at 5 3/2. So we have all that information. Can we write out an equation for this thing? The vertex, well, that's the position of our red dot, which is a shifted position of the origin. You do a horizontal shift, a vertical shift in the origin of your squaring function, which is, of course, what you transform to get a parabola, ends up here. Okay. So we know that the horizontal shift is 5. We got to move from the origin 5 units over. We got to move up 3/2 of a unit. We also have to stretch the thing before we do that. And we don't know what the vertical stretch factor is. So we say, okay, well, let's see. Here's the information that we're going to use. We estimated the parabola vertex at this point, y-intercept is 0, 7. And we start with the toolkit function y equals x squared. And we say, okay, we know we have to stretch this vertically because it's very unlikely that the exact shape of our toolkit function is going to match the shape of this parabola. It's going to have to be stretched this way or maybe compressed. Turns out it's got to be compressed, but it's the factor A that does that. So if A is our vertical stretch factor, it's our unknown vertical stretch factor. When we stretch it, we know we're going to get y equals A times f of x. Okay. Well, we also know that by the time we've vertically stretched and horizontally and vertically shifted the graph, it's going to have the form y equals A f of x minus h plus k. That's our standard form in functional notation for the transform function. Okay. A is our unknown factor. H and K we know because we know where the vertex is. H and K are the coordinates of the vertex. H tells us how far to shift the toolkit function in the horizontal direction. K tells us how far to shift it in the vertical direction. So we know then that since this is a parabola, it's a transformed quadratic squaring toolkit function, right? So f of x is a toolkit function. So we have y equals a, f of x minus h plus k, where f of x is the toolkit function, so that f of x minus h is x minus h quantity squared. We get y equals a times x minus h quantity squared plus k. There's one of our standard forms called the vertex form of a quadratic function. Okay. Well, we know what h and k are, so we write in our h and our k, and we get this equation. And we know that we have the point 0, 7, so we can let x equals 0 and y equals 7, so x equals 0, y equals 7, and we can solve for a. Because plugging in the x and the y coordinates of any point on the graph is going to give us just a bunch of numbers, and the only unknown is going to be a, so we easily solve for a, and if I solved it correctly, a is 11 over 50. In the steps of solving that for a, I skipped a couple of steps. That should be a straightforward solution. Okay, so there you have it. And now our function, we know what the value of a is, so it's going to be a is going to be 11/50, and then we're going to have our x minus 5 squared plus 3/2. Then we want to figure out the solution of the equation y equals 4. We want to know the x values from y equals 4. Well, we translate the equation y equals 4 onto the graph, write the y equals 4 line here, and we get 2 points of intersection. So y is 4 here, y is 4 here. What are the x values? Well, this x value is pretty close to the x minus 1. Didn't get as far as x minus 2, so I just set halfway between 1 and 2, let x equal 3/2. Turned out that was pretty accurate. Okay. And then for this one, well, here's 5, here's 10. It's between 5 and 10, somewhat closer to 10. Let's just say x equals 8. So our estimated solutions are 3/2 and 8. Now we solve the equation. Solving the equation is straightforward. We write out, the right-hand side of the equation and set it equal to 4. That's same as saying y equals 4. Y equals this, so this equals 4. We do the solution, and in doing the solution, I multiplied both sides by 50 here. Now that should be obvious because I keep telling you, if you got denominators in an equation, you usually want to multiply by a common denominator. Multiplied everything by 50, we got this equation. Then trying to solve for x, subtract 75 from both equations to get 125. So 11 times x minus 5 quantity squared is 125. Divide both sides by 11, x minus 5 squared equals 125 over 11. And then I started running out of room, so I had to spread it out over the bottom of the page here, but that means x minus 5 is plus or minus the square root of 125 over 11. And that's approximately plus or minus 3.5. And looking at it, I'm thinking maybe 3.6 would be close, but 3.5 might still be safe. Okay. If x minus 5 equals plus or minus 3.5, I add 5 to both sides. I get x approximately equal to 5 plus or minus 3.5, which gives me 1.5 or 8.5, which agreed really well here. It just, but remember, this is an approximation. The solution isn't exactly 1.5. Okay. And then, or 8.5, which is pretty close to my 8. So now everything comes full circle. Okay. So again, if you want to see that developed a little more quickly or in a little more detail, you can check out the site for the support course. Oh, there it is. Okay. Then what we talked about in the support course was equation solving. So I'm not going to go through all the details, but start with linear equations, and then we talk about quadratic equations, and then exponential and logarithmic equations. Just a quick review to jog your memory. Okay, a linear equation might be something like this. It's just got x's, no x squareds, no square roots, and numbers. And you see, with the equation I've written here, you're going to use a distributive law to multiply out this term. You're going to use a distributive law here. Then you're going to pull your x's together and your numbers, and you're going to get all your x's on one side and all your numbers on the other, and you're going to get a solution. And I'm not going to work that out. Everybody has shown themselves to be competent to solve a linear equation. The one linear equation I do want to solve to emphasize something that I can never get people to understand. So please be the first class that totally understands it. I've got 7 over x plus 3 equals 5 over 2x. Now I can look at that and tell that it's a linear equation, but you might not. You do the logical thing. You do the thing that I keep advocating. You multiply both sides by the common denominator. Denominators are x and 2x. The common denominator is 2x. You got a denominator of 2x, then you've got the x. And you've also got the 2x. So we multiply 2x by both sides. It clears the denominators. I go through a lot of detail on clearing the denominators and all the details of why it works out the way it does. But this equation comes down to the form 14 plus 6x equals 5. And you're going to get x equals -3/2. And maybe that checks out. Okay, we didn't do the check. In practicing problems, preparing for the test, I strongly advocate that you check your solutions, because then you know whether you did something wrong, right there, and then when you're thinking about the problem, and you can fix it, and you can correct whatever type of error you happen to be making. Okay? Now, we get a quadratic equation here. I've written a very similar equation, except the x in the denominator went into the numerator here. So instead of 5 over 2x, I've got 5x over 2. Left-hand side is the same. Our common denominator is still 2x because we need a 2 for this denominator and we need an x for this denominator. So we multiply through by 2x. That's straightforward. And we come down to 14 plus 6x equals 5x squared. At this point, if you're thinking linear equations, you might get misled and you might go around in circles trying to solve this thing. You might even get a solution using techniques for linear equations, but it's going to be wrong. Okay? It's a quadratic equation. I say here, aha, we got x and x squared and a number. Okay? So this can be rearranged into the form ax squared plus bx plus c equals 0. So we rearrange it just by subtracting 5x squared from both sides. We get this equation. And We could try to factor that. I don't think it's going to factor, but maybe. We use a quadratic formula. Okay, that's just an illustration. You got an equation like this, it can lead to quadratic. Because you got an x in the denominator, you got an x in the numerator. When you multiply by the common denominator, you're going to get an x squared. We've seen this before, so mainly I'm just trying to jog your memory and show you the overall picture of what you got to be able to do to solve equations. I'm a little out of order here. Okay, now I did a polynomial equation. Here's a polynomial set equal to 0. The polynomial is already factored. The only way the product of these three factors is 0 is if one of them is 0. So we say, well, this product is 0 if this thing is 0, or if this thing is 0, or maybe if this thing is 0. So we get three equations that we can easily solve. This one, well, the solutions are obvious. This equation, 3x plus 12 equals 0, gives us x equals -4. 2x minus 4 equals 0 gives us x equals 2. And x squared plus 6 can't be 0. Why not? Because x squared can't be negative, and the only thing we could add to 6 and get 0 is -6. X squared can't be -6. Okay? X squared is greater than or equal to 0, so x squared plus 6 is greater than or equal to 6. So there's no solution there. Here's our solution set. It's very simple when you have a polynomial that's factored into linear and quadratic terms. These are linear terms because they give you linear equations. This is a quadratic term. This is actually a quadratic equation. So let's talk, since we've got this solution set, let's go ahead and talk about the graph of this polynomial. Okay, so we want the graph of this polynomial. What do we know? We know that the zeros are at x equals -4 and at x equals 2. So maybe the polynomial looks like the white one, or maybe the polynomial looks like the green one. It can have some wiggles in it because it's of degree 4. I'll talk about that in a minute. So these are both plausible graphs for the function. Okay, the white graph or the green graph. We don't know which it is. And in order to figure out which it is, it's real easy to do 1 month into a calculus course. Okay, turns out it's pretty easy. We then digress into what the graphs of different polynomials might look like. Okay, here's a picture of a parabola. That's a quadratic function of degree 2. It doesn't wiggle in the sense that this thing wiggles or this thing. Okay. What we don't talk about usually is we don't talk about wiggles. We talk about turning points. That's what you've seen. I call them wiggles because then I can say what I said down here. We'll see what I mean. Okay. It's got one turning point. That's the main characteristic. It turns here and that's it. A cubic polynomial has degree 3. Okay. It's a transformed cubic function. Graph of the basic cubic function looks like this, but the cubic function can have 2 turning points. So it can turn here, it can turn here, it can look like this. It could be upside down or backwards, but it's going to have this basic characteristic. And I call those turning points. 2 turning points is equivalent to 1 wiggle. Okay? To wiggle, you can't turn just once, you have to turn twice and you wiggle. If you want to think in terms of wiggles, that's fine. Okay. Now back to this function, which is degree 4. Why is it degree 4? Well, if you do the distributive law throughout, you're going to at some point multiply 2x by x squared to get 2x cubed. And then that's going to get multiplied by 3x to give you 6x to the 4th. So this polynomial is 6x to the 4th plus lower order terms. If you zoom out, you get a y equals 6x to the 4th graph, which I should have drawn a little flatter, but it kind of looks like this. And the main thing about it is that the graph goes to plus infinity on this side, it goes to plus infinity on this side. The long run behavior is toward plus infinity, whether you go to the left or to the right. So we know that these are plausible shapes for the graph of this function. We don't know if it wiggles down here, and we're not going to be able to find out in this course. Okay? But what we do want to know is if you got a degree 4, you can have 1 more turning point. Why? Because you can have 4 zeros. If you got 4 zeros, the only way you're going to go through all 4 of them is to wiggle a couple of times and to have 4 turning points. They don't have to have 4 turning points, but they can have 4 turning points. So I say for degree 4, you have no more than 3 terminal points, and the word is than, not that. No more than 3 turning points, no more than 4 zeros. I keep writing that when I mean than. Eventually I'll be talking Icelandic or something. Okay, make sense? Does this ring a bell? It should ring a bell. And what I'm trying to do today is ring bells because I can't go over every detail of the course. I give you an overview, give you as much detail as I can. Okay, another thing about zeros, since I'm digressing here. Okay, any of these shapes, the orange one or the yellow one or the blue one, can represent a degree 4 polynomial. They would all have different formulas, but they'd all have an x to the 4th term out in front, and it would be a positive x to the 4th term since they all end up going toward plus infinity on both sides. Again, the zoomed out would be the y equals 6x to the 4th function, but with wiggles close to the y-axis. So you go back, take whatever this function is, whatever one of these functions is, zoom back. You're always going to have something like the 6x to the 4th. Okay. And the cubes and the squares and the first powers and the constant numbers don't affect that. If x is big enough, 6x to the 4th is so much bigger than everything else, everything else becomes negligible. All right. Another thing, take this shape or this green shape. If we lift this shape up a little bit, we could get this point to hit the x-axis and we'd have a 0, right? So all we've got to do is add some number, and it'd be a number you don't know how to determine at this point. Again, you need calculus. Add some number to whatever you get when you expand this, and you get a formula for a polynomial that just touches the x-axis here. And it touches the x-axis like a quadratic function. Take it up a little higher, and maybe this one will come up to where it just touches the x-axis. Okay? Just refresh you're remembering the idea that if you do that, the last thing I just said, so that this thing touches the x-axis, what do you get? You get a zero here, you get a zero here, and you get a zero here. This zero has multiplicity too, because it acts much like a quadratic. And we've been through a lot of details on why that is. But you don't really have to know. You don't really have to be able to totally explain that, but it helps if you understand what I've told you, okay? Which is basically just that if we're real close to the point where this thing touches, you have a quadratic factor and all the other factors don't change much between here and here. So it pretty much acts just like a vertically stretched quadratic. Okay, now I haven't said everything and there are too many words to say that they would get lost in the confusion. Here and here, it acts linear. Whether it acts like a quadratic or linear at a zero depends on the degree of the factor. Okay, if we had a 3x plus 12 squared factor in a polynomial somewhere, then at x equals -4, we would have a quadratic zero. Okay, you would touch it like a parabola. If we just have a 3x plus 12 factor, well, as it does here, it goes through, and in the vicinity of this zero, it acts like a straight line. It's really curving a little bit, but if you look real close to here, you can't see the curvature. Okay, you could calculate it, but you can't see it. So that's kind of a little overview of polynomial equations. We go ahead and solve a polynomial equation somewhere. Since we've already got a polynomial, okay, now we're still talking about the polynomial here that's given by this expression on the left. I'm sorry. No, we aren't. Sorry, I just made one up. Okay. What you do if the polynomial is already factored, it's pretty straightforward to construct its graph if you understand the rules and if you practiced it. If the polynomial isn't factored, then in order to find the zeros, you got to in some way factor it. So we take this polynomial and we try to find a value of x that makes it zero. The first value of x I usually try is 1. And I set this up so that 1 works. Okay. If 1 doesn't work, try -1. That doesn't work, try 2 or -2. Maybe even 3 or -3. If I say factor this polynomial, it's going to be one of those numbers. And it won't be bigger than 3 or -3. Okay, be between -3 and 3. Okay, if I plug in 1, I get 2 minus 5 plus 7 minus 4. Well, 2 and 7 makes 9. Minus 5 and minus 4 makes -9. So that gives me 0. So by inspection, we find that x equals 1 is a 0. So what do? We divide x minus 1 into the polynomial, knowing that we have to get a quadratic result with no remainder. So we do that long division. Now I've done it here. Everything except putting the little reminder signs. And we've done enough of that. And, you know, if you practice doing the long division, it's not difficult. This goes into this. The x minus 1 goes into our polynomial this many times, 2x squared minus 3x plus 4. That means that this polynomial equation becomes this equation where we've got x minus 1 here times the quotient 2x squared minus 3x plus 4. equal to 0. So rewriting that equation, setting equal to 0, we see x minus 1 is 0, or 2x squared minus 3x plus 4 equals 0. Well, we solve those equations. Easy to solve this one. We're going to get x equals 1. How do we solve this one? Well, we can use a quadratic formula, and we find that we get no solution because we get a negative under the square root. Okay. We could have done the b squared minus 4ac on this thing before we wrote it all out. We'd have just done the 3 squared minus 4 times 2 times 4 and found that it's negative. We know we're going to have to take the square root of that, so we don't even necessarily have to write out the whole quadratic formula to determine that we have no solution. Now, if we get 0 or a positive number under the radical, the b squared minus 4a squared is 0 or positive, then we do want to use a quadratic formula to find where the zeros are. Okay, so that's kind of it. So the solution to this is just x equals 1. Solution set is just the set containing the number 1. And if we zoom out, this is a cubing function. It acts like, oh, I got all kinds of, it acts like 2x cubed. And the y-intercept is at 0, negative 4. That's obvious. Y-intercept occurs when x equals 0, something you can't forget. Plug in 0 to this expression. These three are all 0. You get negative 4. Here's your y-intercept. Here's a graph. It acts like 2x cubed, which would be this function, meaning it goes down over here and up over here. So there are our arrows indicating the long run behavior. We've got to go through the y-intercept. We've got to go through the x-intercept. So it might come up like this, start to level off a little, then decide, oh, let's just curve on up and go. Okay, we don't know for sure what it does in here, but overall, it's going to have this behavior. Make sense? Okay, now we're going to, yeah, sorry you have to go because we're going to do some stuff you didn't see.
I know it's the video. Gotta go get my son.
Yep, that's priority. Okay. Make sense? And we have exponential equations. Here's a typical exponential equation. And then here's going to be a typical logarithmic equation. We have the rule equivalence between exponential and logarithmic form, which you simply have to know and have practiced. If you've done the problems with this in front of you and on every problem, you probably don't remember it. If you put it away after doing a couple problems and remembered it, then you probably remember it a lot better. Okay. Exponential equation, typical, is like this. What we want is something we can put into this form or that's in this form or this form. We want some number to the some power equals c. Since what we're looking for is in the exponent, that's what we do. We try to isolate the 3 to the 5x minus 7 term, set it equals something, and we easily do that. We subtract 9 from both sides. We divide both sides by 4. And we get 3 to the 5x minus 7 equals 7/4. We rewrite that in log form. We get log base 3 7/4 equals 5x minus 7. And then we switch sides, so x will be on the left, which is where we're probably used to seeing it. We get this. Okay. Add 7 to both sides, we get 5x equals log 3 5/4 plus 7. Divide both sides by 5. Well, here's what we get. And log 3 of 5/4 is the log of 5/4 divided by the log of 3. So I'd want to see all the steps down to here before you plug it into your calculator. Okay? Ideally, I see the exact solution. So this is exact. The approximate solution. Can't see that word, that's calculator. Okay. So I want to see an exact solution. But then an approximate solution is always good too, because you can take your approximate solution, plug back in and check your work. Logarithmic equations. Here's a typical logarithmic equation. Okay. We got the 3 log base 4 of x minus 4 is the same as log base 4 of x minus 4 to the third, just using your rules for logarithms, which you need to know. And then it's a log base 4 of this plus a log base 4 of this, which means it's a log base 4 of this times this. Again, applying the rule. Then we switch to exponential form and we get 4 squared equals x minus 4 cubed and so forth. You'd see it there. Flip side, so the x's are on the left, we get this. Then we would expand this and put it into the form p of x equals 0. It's going to be a 5th degree polynomial, and you're not going to be likely to find zeros unless I contrive it. Okay? So I say, put it into this form p of x equals 0, then good luck. Yeah, on this equation. Now, if I didn't have the 3 in front here, and if this x wasn't squared, then I would just get a log of x minus 4 times x minus 9, which is quadratic. And I'd have a quadratic equal to 16. And I could put that into the standard form of a quadratic, either factor or use quadratic formula. So that's kind of a survey of how you'd solve most of the equations that could arise. So now I want to talk about well, actually, let me check something real quick. I think I've already done that. Okay. There's a rectangle, 4 units wide. Let's say y equals 6 here. And y equals 38 here. And we've got a straight line. Now, eventually we might want to put an exponential curve in here, but we're going to do a straight line in the lower left corner. Up to the midpoint of the right edge. What's the equation of the straight line? Well, give you a chance to tell me. Okay. Now we want the equation of a straight line. We need either 2 points or a point of a slope. Well, we've got 2 points right here. All we have to do is figure out their coordinates. This is the line x equals 12 in the middle. The width of this rectangle is 4. So this line must be x equals 10. This line must be x equals 14. The only way it's going to have a width of 4. By the construction, this point is in the middle of the lower edge. Lower edge is 4 units wide, which means that this point is 2 to the left and this point is 2 to the right of the red dot. So that is something you absolutely need to be able to see, just be able to do the geometry of a fairly simple rectangle in the plane. And from that, you can determine that this point is at x equals 10, y equals 6. This point is at x equals 14, and y equals what? Well, might have to do a little work to figure out what y is here, but from 6 up to 38 is 32 units, right? So from here to here is 32 units. This is a line halfway between here and here. So from here up to here is going to be 16 units. This is y equals 6. That's going to be 1422. Now, if you use one of the standard constructions, you need to be able to label the construction lines. If you know where the red dot is and you know the dimensions of the thing, or if you know some of the lines and the boundary and so forth, you can figure out all the rest. And I expect you'll need to do that. So be sure you understand how that's done. So the points are and 6 and 1422. Now we could find the slope and use one of the points in the slope and get the equation. We want to do it using simultaneous equations though. Form is y equals mx plus b. So the point 10, 6, y is 6, x is 10. So we're going to get 6 equals 10m plus b using this form. And the point 1422 gives us 22 equals 14m plus b. So we want to solve for m and b. Write the system out again. Now I'm going to write the system as and m plus b equals 6. 14m plus b equals 22. This is equation 1. This is equation 2. If I do equation 2, minus equation 1. And remember, I'd say write that out to the side. So equation 2 is 14m plus b equals 6. Equation 1, negative equation 1 is 10m, negative 10m minus b equals minus 16. Now adding equation 2, the negative of equation 1, we get 4m equals negative 10. Okay, I've got the numbers over here wrong. 14m plus b is 22. And then the negative of this equation gives us negative 6. So 4m equals 16. M equals 4. So we get M equals 4. Plug that back in. And it gives us the equation. N plus 4. N times 4 plus b equals 6. Something is a little bit amiss here. No, it's okay. All right, so that gives us 40 plus b equals 6. B equals negative 34. Y equals 4x minus 34. And that works out. Okay. Now we could have solved using the augmented matrix. The augmented matrix would be 10, 1, 6, 14, 1, 22. So this is row 1, this is row 2. To reduce the augmented matrix, we do row 1 divided by 10, which gives us 1.1 and 0.6. We keep row 2 the same. Then we do row 1, which we're not going to mess with. We do row 2 minus 14 times row 1. Because we multiply this 1 by negative 14 and then add to the 14 here, we're going to get a 0. And that's what we want. We're going to get 1.1.6. We're going to get 0 here. Now, 14 times 0.1 is 1.4. And subtract that from 1, we're going to get negative 0.4. And that's 6. 22 is negative 16. Without writing out the details, although we would want to write them out off to the side someplace, we get this. We would divide row 2 by negative 0.4, dividing negative 0.4 by negative 0.4. It's going to give us 1. And the reason we divide by this is because we want 1 here. And we get 40. So again, we see the process. We want to get a 1 in this position, then we want to get a 0 in this position, and then we want to get a 1 in this position, without messing with the 1 and the 0 we already have. Okay? And that's easy in this case. We just divide by whatever this number is. And then we subtract 1/10 of this row from this row. And something's not going to work out. I'm going to check my equations. They're correct. So I'm not going to belabor any error here. I have to take row 1 minus 0.1 times row 2. And I keep row 2 here. And when I do that, 0.1 times 1 is 0. Problem comes over here. 1/10 of 40 is 4. 40 minus 6 is 2.4. And I'm supposed to get 4 there. I need to get 4 there. So something is wrong somewhere. But all I've done to this row is divided it by 10. That's got to be accurate all the way down. This row gives me I think I made a mistake up here. Yeah. Okay. Process is correct, but I got a bad number up here, and I probably should have written this out. 14 times row 1 gives me an 8.4 here. And these numbers were wrong. Apologize for that. Okay. Subtracting 8.4 from 22, gives me $13.4. Yeah. Then I'm going to get 34 here. So now when I subtract a tenth of row 2 from this, I'm subtracting 0.3, 3.4. Should be a negative 34. I'm adding 3.4 to 6 and I get 4. Okay, sorry. Okay, now what I want you to see, and sorry for the delays, I want to get through this kind of quickly, is again, we get a 1 here, then we get a 0 here, then we get a 1 here, then we get a 0 here, and now we have a solution. X equals 4, y equals negative 34. Shouldn't have put that decimal in there. And this agrees with what we got over here. So you could reasonably expect to get a problem like this. I think maybe the right side of the board wasn't visible. I wasn't checking. Just to review, we started with the red dot, width 4, the line y equals 38, and the line y equals 6. From that information, and the fact that this is a line x equals 12, in other words, we were given this, 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 and this, we figure out everything else. Figure out all the coordinates of this point and the coordinates of this point, so we can get the equation of the line using simultaneous equations. We could also have gotten the equation of the line using the coordinates of either one of these points and a fundamental triangle, which would have given us a slope. Okay. So that's fairly straightforward. What I'm really trying to emphasize here is how to use the simultaneous equations, elimination, and then matrix methods to get the equation of the line in 2 different ways. Okay, I'm going to do another thing here. I'm going to construct an exponential function in this rectangle. So now, there it is. Exponential function. Exponential function. At this point, uh-oh. Never mind, I'm not going to do that. Okay. Give you another. Another grid. First thing, I want you to draw the quadratic shape in a window. So we know that we're going to divide the window down the middle vertically and horizontally, which among other things is going to give us a red dot. We don't know what the equations of these lines are yet because I haven't given you any information. We're just constructing the grid and the shape, and we'll put numbers on it in a minute. So we do the rest of the construction. Draw ourselves 5 horizontal lines, starting the line halfway from the top to the bottom, get the middle line, then halfway from there to the bottom, halfway from there to the bottom, halfway from there to the bottom, halfway from there to the bottom. Vertical lines halfway between the right edge and the middle, and then halfway between that point and the middle. And then same from the left edge to the middle, halfway from the left edge to the middle, halfway from that point to the middle. And there's a grid that will allow us to construct a nice quadratic function. Start at the upper left, move 1 right and 2 down, 1 right and 2 down, 1 right and 2 down puts us at the red dot, 1 right and 2 up, 1 right and 2 up, 1 right and 2 up, gets us over to the top. Should have been a little flatter down here. Okay. And now we're going to construct a straight line. I'll just go from the lower left edge, the lower left corner, to the middle of the right edge. And there's a straight line. I'm going to give you the dimensions. I'll make it 4 units wide, that's easy. And just for illustration, I'll make it 4 units high. Put the red dot at the point 12. -8. And then we label the rest of the construction lines. Okay. This line is x equals 12. So you get that a little more stable. This line, I think, is 4 units wide. Half of 4 is 2, so we move 2 units to the right of x equals 12, and x equals 14. Here we get x equals 10 here. Happens to be the same numbers we had in the previous exercise. Okay. We know that y equals -8 here, because -8 is the y coordinate of this point. Thing's 4 units high. So if we go up 4 units from -8, we get to -4. And now halfway between -8 and -4 is -6. Halfway between -8 and -6 is -7. We have -7.5. And then we have -7 3/4, -7 7/8, which we don't really need in this case. So I'm not going to take the time to label them. But again, halfway between -7.5 and -8 is -7 3/4 and all that. Okay. The X, these lines, well, here's X equals 11. Here's X equals 13. And now I've got a pretty well labeled grid. I want to find the equation of this straight line. The points of this point is y equals -8, x equals 10. -14, -6. I could do simultaneous equations. I could do augmented matrix as we did previously. Yeah, I'm just going to say we're going to use the slope. Fundamental triangle is going to have a run equals 14 minus 10 equals 4. Rise equals -6 minus -8, which is 2. Slope is rise over run, which equals two over 4, which is 1/2. Y equals mx plus b, so y is 1/2 x plus b. Take either of these points, y equals -8, when x equals 10. So -8 is 1/2 of 10 plus b, just plugging in -8 into 10 for x and y. And we solve this. Half of 10 is 5, subtract it from both sides. B equals -13. So the equation of the line is y equals 1/2 x minus 13. We can check this out. If x equals 10, half of that is 5, and 5 minus 13 is -8. So when x equals 10, y should equal -8, and that works. And it's also going to work if we use the coordinates of this point. I'm not going to go through that, but you plug those coordinates in and double check to make sure that's the right equation. Okay, now the equation of the parabola. H and K are 12 and -8. using the point. Yeah, something's wrong here. No, it isn't. We get A equals 1. So we have y equals x minus 12 quantity squared minus 8. What I want to do is I want to find the points of intersection. I want to find this point and this point. I can estimate these points. This looks like x equals, if this is 11 and this is 12, this is about 11.1. This is x equals about 13.2. We get the intersection when y equals 1/2 x minus 13 and y equals x minus 12 squared minus 8. So we set these two quantities equal and solve for x. Expanding x minus 12 squared, we get x squared minus 24x plus 144 minus 8. That's equal to 1/2 x minus 13. Subtracting the 1/2 x minus 13 from both sides. Actually, I don't want to work with fractions. I'm going to double both sides. We multiply by 2, get this. Multiply out the fraction. We get this. Subtract the x from both sides. $272 and 26. You believe we get this? We're out of time, so I'm not going to simplify this, but I'll pin it on the end of the video. And what we should get is something pretty close to 11.1 and 13.2. So I'll do a little more explanation of these steps in the video. We're over time. I don't want to hold you up any longer. Although if you want to stick around and watch me append it, you're welcome. But if you got to go, please go on. I'll put it onto the video. Okay, it was a little rushed toward the end there because we were actually a couple of minutes over time on the class. But what we're doing is we're trying to find the intersection of this curve with this straight line. So the intersection, we figured out the equation of the parabola. We did that in some detail. We figured out the equation of the straight line. We checked out the equation of the straight line. I believe the equation of the parabola is exactly what I expected it to be. But here's how we would do it. So we set if y equals this and y equals this, then this has to equal this, and there's the equation that expresses that. The solutions to this equation will be the x coordinates of these points, which I've estimated to be 11.1 and 13.2. Now, it's doing a lot of arithmetic kind of fast, so let's make sure I did it right. Okay, first we have this. Now, we expand. And we get this. By expand, we mean we expand the square. Okay, then we simplify. So we expand, we get this. We simplify, we get this. No, I'm sorry. I say we multiply by 2 because that's a denominator. We multiply by 2 here on both sides. Now it's implicit when I say multiply by 2. I mean multiply both sides of the equation by 2 because we multiply them by different numbers. We multiply one side by 2 and don't multiply the other by 2. We're not going to get an equivalent equation. Okay, but if we double both sides, we do get an equivalent equation. And all I've done is I've taken every coefficient here and doubled it. Okay, so x squared becomes 2x squared. Negative 24 doubled is negative 48. 144 doubled is 288. 8 doubled is 16. Double 1/2, you get x. Double 1/2 x, you get x. Double negative 13, you get negative 26. Now then we simplify. I think what you do is obvious. We just put this in standard form. Now I did the 288 minus 16, which gave me 272. I add 26 to both sides. 26 and 272 gives me 298. I add a negative x on both sides, gives me negative 49x, starting with negative 48x. So I think those numbers are correct. And then I said, okay, I put that into the quadratic formula. I said, class needs to be able to go home about 3 minutes over time. Okay, so I'll do the arithmetic or the approximate arithmetic. Okay, 49 squared is 50 minus 1 squared, which is 2,500 minus 100, which is 2,401. Okay, now that's like negative 4 times 300, which would be negative 1,200. But it's going to be 8 less than that, make it minus 1192 over 4. It's going to be 49 plus or minus, then the square root of is going to be 1,200 I think it's right, 1,209 over 4. And now I'm going to have to approximate. I'm going to get 49 plus or minus. Okay, the square root of 900 is 30, square root of 1,600 is 40. So I'm going to say, that's going to be pretty close to 35. And I'm not getting anything close to my estimates. It's something that is screwed up. And it's not my estimates. Maybe it's one of my equations. Maybe it's my arithmetic. Oh, it's 40. Well, we're dividing by 4, not by 2. Okay, 49 and 35 is 84. (49 minus 35 is 14 over 4. It's not going to help much. And I don't know what went haywire. I did stuff kind of quickly up here, but I just double checked it and it seems to be okay. So I'm going to pause the video and see if there's something I need to repair. Obviously there is. Okay, I was very careless when I wrote down the quadratic formula. It's supposed to be 4AC, A is 2, C is 298, but I should have had a 4 here. Now, this number is going to be twice as great, which is going to be 2386. And this becomes about 15. And I think that's going to work out pretty well. Square root of 15 is about 3.8. It's between 3.8 and 3.9. I'm choosing 3.8. I think it's probably right. So that's 52.8 divided by 4, using the plus, or 45.2 divided by 4, which equals 13.2 or 11.3. Now, looking at my estimates, of 13.2 agrees. So I constructed this thing reasonably carefully. I didn't expect to get the thing actually to the 10th. And then I've got 11.3 when I estimated 11.1. So you see that, I'm off by 0.2 between the two of them. So, kind of close. And at this point, I'm pretty confident in this solution because it matches the numbers that I got here quite well. Okay, so you have the whole idea of the intersection of two curves. Now you've done intersection of two straight lines. And of course, you can extend that to the intersection of two curves. You've got two straight lines, you set their equations equal to each other. Okay, you solve that as a set of simultaneous linear equations. In this case, you have simultaneous equations, but these are not linear. They're not both linear, so you can't use elimination. You can use substitution, which is what I've essentially done. I said y equals 1/2 x minus 13. So I've substituted that for y here, and I got this equation, solved the equation. Did a careless thing here, but when I worked out everything, and you can check my numbers. I'm not sure that 2386 is right, but I'm pretty sure because it worked out so close. Okay, so that's a process, and that's something you can expect to see on an exam, probably a straight line intersecting with a parabola or a straight line intersecting a straight line.